What we had started was we had started doing halogenoalkanes, right? Halogenoalkanes were that you had a carbon chain which had chlorine and fluorine and bromine and iodine halogens in it. And we talked about the properties that they were polar molecules. They had dipoles and they would attract each other. And sometimes the dipoles would also cancel out if there were too many halogens, like chlorine and all the dipoles, their attraction getting cancelled out. So sometimes they do cancel out as well. And they're not soluble in water, or you can say they're very slightly soluble in water because water forms hydrogen bonds and they are not capable of forming hydrogen bonds. Then we talked about the formation of halogenoalkanes, which was free radical substitution of alkanes, electrophilic addition of alkanes, which we have already done, like bromination. And then we started talking about nucleophilic substitution of alcohols, that you could get rid of the OH and substitute the OH with Cl or with Br or with I. And there were multiple conditions for the reactions. You could use PCl3 plus C, you'll get a Cl instead of the OH. Red phosphorus plus bromine, that would give you a Br instead of the OH, and you had iodine. And then we started talking about the nucleophilic substitution reactions, which was kind of the opposite, which was that you have a halogen, and that halogen can get substituted by three things. OH minus 1, it would form an alcohol. Cn minus 1, it would form a nitrile. This one over here is a nitrile. Let me name them as well. This over here is an alcohol, and you can also get amines. You can add NH3. And I told you that the CN reaction was special because the number of carbon atoms would increase if you add a CN. I said, then we started talking about the mechanism of the reaction, and specifically this nucleophilic substitution reaction mechanism. The mechanism for this reaction was that there were two mechanisms. One was that there was a primary halogenoalkane. Now, in a primary halogenoalkane, what's a primary halogenoalkane? That the alpha carbon, or the carbon which is bonded to the functional group or whatever, like in this case, it's bonded to chlorine, would only be bonded to one carbon chain, and on two sides there would be hydrogen atoms around it. And the mechanism for this reaction was, you'll be asked to draw this mechanism. This was the mechanism that the nucleophile, which was over here, there were three nucleophiles. These are your nucleophiles. So the nucleophiles, which could be OH minus 1 or CN minus 1 or NH3, these were your nucleophiles. They would get attracted to the positive carbon atom over here. And they're going to get attracted because this is a polar bond. And when the negative nucleophile are things that are attracted to positive things. So when the nucleophile would get attracted, and the negative charge would come in, try to bond with the carbon atom. At the same time, the electrons over here are going to get repelled, and there's going to be a transition state. This over here was your transition state that was happening. So transitioning would happen. That the OH would come closer and closer to this carbon atom, and the Cl would eventually get knocked out. And at the end of the day, the OH would take the place of the Cl, and the Cl minus 1 would have been knocked out. Okay, so that was a simple mechanism. You just have to get all the arrows and the curly arrows and the partial positive and the negative charges. You have to get that right. You have to make them correctly. Okay, so that's the mechanism of the reaction. Uh, the other thing about this reaction was that it was a one-step reaction. Like you can see a couple of steps here, but it's a one-step reaction. What that means is it's a one-step reaction. What that means is that so what that means is that this reaction is just a transition happening. You have your reactants and then you have your products. I mean, this is just a transition state. You don't actually get this. So, I mean, this is nothing that's getting formed. It's all happening in one step. The OH comes in and the Cl gets knocked out. So the OH comes in and the Cl gets knocked out. So you're just showing how the transition is happening. And the energy profile diagram for this for a one-step reaction would look like this. Like it just has one step, so it's going to be reactants, and the reactants would change into products. Whether it's endothermic or exothermic, that's irrelevant, and that's going to vary from. It depends on the halogen. It depends on the nucleophile. So this is your reactant, and that's going to be your product, and that's your energy axis. Plus, this is where the transition would be happening, right at the top. This is where the transition state would be that you have a carbon chain, and you have H, and you have another H, and there would be a nucleophile that would be trying to bond with it. Let's call that Nu. And there would be a halogen that would be trying to go away. So there's going to be so this is your transition state somewhere over here. The transition would be happening. So that's your transition state. I said now another mechanism is for the same reaction. There's another mechanism. It's the same reaction, same nucleophilic substitution reaction, and that's called an SN2 mechanism. This one was an SN2 mechanism. Reason why it's called 2 is that the rate of the reaction depends on both reactants. Okay, so why is there a 2? So 2 in SN2. Why is there a 2? The reason there's a 2 is that the rate of the reaction depends on the halogenoalkane because it's a one-step reaction. So it depends on the concentration of the halogenoalkane plus the concentration of the nucleophile, which in this case is our OH nucleophile. So rate depends on both reactants. It depends on both reactants. Now that's fairly obvious that you have a reaction. You have one molecule of a halogenoalkane and you have another molecule of OH minus one, which is your nucleophile. Uh, if you have higher concentration of both, then obviously the number of collisions that they can have or the number of interactions that they can have would obviously increase. You have more OH ions, there would be more chances of the OH ion bumping into this or getting attracted to this positive carbon atom. Or vice versa, if you have more halogenoalkanes, you know from O levels that if you increase the concentration, the rate of the reaction increases because the number of collisions that they would also increase. Okay, so that's why it's called SN2 because the rate depends on this as well. It depends on this. It depends on the concentration of both reactants. Now we're going to start talking about Ibrahim. I think your mic is on. Yeah, the clear. Abba, is this clear?
Sir,
Huh?
I just want to ask SN2 mechanism primary alcohols में होता है?
The primary halogenoalkanes.
अच्छा, primary halogen, and any reason for that?
Well, I'll discuss the reason shortly. Okay.
Yes.
I'm going to talk about the other one now, and that's your SN1 mechanism. Okay. Now the SN1 mechanism happens where it happens with tertiary halogenoalkanes. So tertiary halogenoalkanes. What's a tertiary halogenoalkane? That is, okay, it's going to be a carbon atom in the middle, and on all sides there would be carbon chains. There's going to be carbon chain over here. There would be a carbon chain on this side. Let's say CH3, CH2, and there might be a carbon chain on this side as well. And you have a Cl. So that's a tertiary halogenoalkane. So alpha carbon is surrounded completely by carbon chains, by three alkyl chains. Now, what happens here is that if I have a tertiary halogenoalkane, what's going to happen is, let's say this is my tertiary halogenoalkane, and it's reacting with the nucleophiles OHCN or NH3. Now, what's going to happen here is that this bond is polar. Carbon is partial positive and Cl is partial. It's partial negative. Okay, so the bond is polar, and you have your nucleophiles coming in. You have your OH minus one. Let's talk about OH minus one. The other nucleophiles are Cn minus one, or you have your NH3 nucleophile, right? So these are your nucleophiles. Now, what's going to happen here is uh, that the nucleophiles would not play any role initially. Initially, what would happen is that the Cl bond would break on its own. So that's the first thing. The electrons over here, they're going to heterolytically there's going to be heterolytic fission, and the bond is going to break completely on its own. Okay, I'm going to discuss why that happens in a just shortly. Okay, so there's carbon and there's CH3, and you have another CH3, and a carbocation is formed. The carbon gets a positive charge because the Cl minus one has broken off. Okay, Cl minus one is electronegative; it wants electrons, so it takes away the electrons in the bond and goes away. And now, in the next step, the nucleophiles, which in our case is OH minus one, they're going to come in and they're going to bond with that. They're going to get attracted to the positive carbocation. The other ones are Cn minus one, or it could be NH3. So they're going to come in, they're going to attack the carbocation, and when they attack it, they're going to bond with it, and that's how you get your molecule. So the final thing is that the carbocation CH3, it now has an OH attached, and the Cl minus one has broken off. So I'm going to rub these off. They have no role in the first step. That's your first step, and then you have your second step. This is your step one. Now this is a proper two-step reaction. You have a step one, and you have a step two. The first step is the slow step. Why is it a slow step? Because it's going to take time for the Cl to break on its own. I mean, there's पिछले case में ना there was someone helping Cl to Cl to break off. I mean, the OH minus one was coming in and directly bonding to the carbon positive, and the Cl, because of the repulsion of this negative charge, was getting repelled. So there was the nucleophile that was pushing the Cl away. But now what's happening is that the Cl has to break on its own. There's no one pushing it. So it's going to happen at a very slow rate. But once that happens, the carbocation that is formed, it would immediately get attracted to the OH minus one. So this one, the next step is your step number two is going to be your fast step. Okay, is this clear? Abba, is this clear? Rida, Hiba, Ibrar, is this clear?
Yes.
Yes, sir.
Achha, so step one is a slow step. Step two is the fast step. Uh, अच्छा, अभी तक we haven't discussed why this happens. ठीक है, we're going to come to that. So this is the mechanism first for tertiary halogenoalkanes. And the other thing is, why is it called SN1? अच्छा एक तो ये proper this is a two step reaction, and you have a carbocation intermediate. So this one is there's a carbocation actually forming over here. So you have a carbocation intermediate that's formed. Two-step reaction का जो process है, the energy profile diagram looks like this, that you have uh, step one, an intermediate is formed, and then the product is formed. So it's going to look like this, that so it's going to happen in two steps. Reactants, and then there's your carbocation intermediate somewhere in the middle. It's an actual thing that is formed. You can stop the reaction at this point. And the final thing is your products. Remember that the second height must be smaller than the first height, because the second step was actually the faster. So it has a lower activation energy. The first one was the slow step, it had a higher activation energy. And this is your energy axis. So why is it called uh, SN1? The reason it's called SN1 is, so 1 in SN1. Why is there a 1 in SN1? That means that the rate of the reaction depends on only one reactant. So rate over here, although there are two reactants in the equation, but rate depends on only one reactant, which is halogenoalkane. I mean, it doesn't depend on the concentration of OH ions. So rate depends on the halogenoalkane concentration, but doesn't depend on the OH ion concentration, which was the other reactant. No matter how much
So,
you, huh,
why is this so okay? It doesn't depend on OH, even the OH ions are present over there in the solution.
ठीक है. So why does it happen? The reason
Mm.
that happens is
Mm.
it's because of the speed of the two steps. ठीक है. The first one is the slow step. So let's give it some hypothetical time. Let's call it that it takes 100 seconds for step one to happen, right? And the second step is your fast step. Let's say it takes 1 second for the step to happen, right? Ibrahim, is this clear? So what's
Yes.
the total time required for the reaction to happen right now?
101 seconds.
That's a 101 second, right? Now, assume that you have increased the concentration of OH ions. So let's say in the second step, there are now a lot more OH ions,
Mm.
right? So you have a lot more OH ions. So what would happen to the speed of the second step?
It would most probably fasten even more than what
Yeah,
it
so
was.
so you have more OH ions, right?
Exactly.
I mean, the speed of the first step would remain unaffected, right?
जी. लेकिन my question is कि why doesn't the OH ions bind in the first step to the
अच्छा,
carbon?
वो तो अभी आते हैं. I'll talk about that. ठीक है. अभी तो I'm just talking about कि why does it. अभी तो I'm just explaining कि why does it. Uh, why does it depend? Why does the speed of the reaction depend on just one of the reactants, not on OH ions? ठीक है. अभी तो
जी.
अच्छा, speed. Second step would speed up, right? Uh, First step, OH ion has nothing to do in the first step, right? So the first step would remain unaffected. Let's go the 100 seconds. It's going to take 100 seconds for the first step, right? But the second step would speed up. Let's say you've increased OH ions and the speed is so fast now that it takes 0.0001 second. Okay, so the second step has really its rate has increased. what is the effect on the overall speed of the reaction? Ibrahim, what is the difference that you're getting now? Previously, it was taking how much time? It was taking 101 seconds.
101. G.
Previously, it was taking 100 seconds for the first step and 1 second for the second one. So it was taking a total of 101 seconds.
G.
Now, if you've increased OHI in concentration, let's say you increase it a million times, this takes 100 seconds and that takes 0.001 second. So the amount of time it's taking is still approximately 100 seconds, right?
G.
So the overall speed of the reaction pretty much remains unaffected. Well, the effect is there, but it's very, very small.
ठीक, get it.
Okay? And no matter what you do, no matter how much you increase the concentration of OH ions, okay, you take it to a billion times, you increase it a billion times. Let's say this speeds up so fast that it goes to 0 seconds. It's still the overall speed of the reaction would still take 100 seconds. So the rate is actually dependent on always on the slow step, never on the fast step. Okay? It's like a relay race where uh, uh, if one runner is very fast and one of the runners in the relay race is very slow, no matter how fast you make the fast runner run, it's the overall time or who's going to win the race. It doesn't depend on him. It depends on the slow one. You have to change that. Okay. So that's why the OH minus one has nothing to do with rate. Okay. Abba, is this clear? Hiba, Rida, is this clear?
Yes.
Acha, so if you increase the halogenoalkane concentration, then the slow step would speed up because there would be more molecules of halogenoalkane, there would be more particles, there would be more collisions, and more chances of the Cl breaking off. So if it goes from 100 seconds to 50 seconds, then there's going to be a drastic change in the speed of the reaction. So it only depends on the concentration of the halogenoalkane. I said now the main thing. Okay, why do they have different reactions? Why SN1, why SN2? So why SN1 or SN2? Okay, why does it happen? First notice the difference. Difference is primary halogenoalkane, the nucleophile is attacking the carbon directly and it's pushing the Cl away. Okay, that's what happens so it's a one-step reaction. The OH just comes in directly and pushes the Cl away. Tertiary halogenoalkane, uh, the Cl has to break off first. The OH is not going to do anything. Once it has broken off and a carbocation has formed, only then would the OH come in and bond with the carbocation. So why is this happening? The reason it's happening is I'm going to draw. I'm going to draw a primary halogenoalkane and I'm going to draw a tertiary halogenoalkane. There's going to be something something different between the two, and that's the polarity. The polarity is one of them is primary, the other one is secondary. Both of them are polar molecules. This one is partial positive, and this one Cl is partial negative, right? Over here as well, carbon is partial positive and Cl is partial negative. So both bonds are polar. Hypothetically speaking, the OH minus one nucleophile it should be attracted to this positive carbon atom. And the OH minus one nucleophile over here should also be attracted to the positive carbon atom, right? Uh, but in a tertiary halogenoalkane, it's not. So why is it attracted to the positive carbon atom over here in the primary halogenoalkane? The reason it's attracted to this positive carbon atom is that this positive charge is actually kind of bigger. This bond is more polar. What's the reason for that? The reason for that is that
Inductive effect.
that is because hydrogen just has one electron, and this over here is hydrogen with one electron, right? Carbon on this side has 6 electrons, so it's going to try and pull electrons from all sides. but there are, I mean, it's surrounded by electrons, but not a lot of them. Hydrogens don't have a lot of electrons. They just have one electron. But this other one, I mean, it is completely surrounded by carbon chains. 6 electrons on all sides. Like the immediate neighborhood, they have 6 electrons. So there's a lot more electrons available. So why would it attract electrons from the OH minus one? I mean, there's no need for it. I mean, it has so many electrons around it that it's going to try and pull the electrons from those carbon chains. Carbon chains have electron donating inductive effect because carbon chains have a lot of electrons. So whenever a carbon chain is attached to anything, electrons uh, can be pulled away from the carbon chain. So the positive charge over here is small. Is this clear, Abba, Rida? Is this clear? Ibrar, is this clear?
Yes.
Yes.
Achha, on the other side, so the difference is if the carbon is bonded to more hydrogen atoms, the hydrogen atoms don't have electrons in the first place. So the positive charge would be kind of very large. And if there are too many carbon chains around it, the positive charge would be small because the electrons would be pulled from the carbon chains to, and they would kind of neutralize the positive charge. So this one is small, which is why it's not interested in the OH minus one. It's not really interested in the OH minus one. This positive charge is very strong, so it's highly interested in the OH minus one. So the OH minus one gets attracted very easily. And you can think of it the other way as well. The other way is that since the positive charge is very strong over here, the Cl minus one would not break off because the Cl minus one would also be very strongly attracted to it. I mean, it's even if the bond breaks, the Cl minus one, I mean, the chances of it just breaking off and leaving are very, very small. So somebody has to push the Cl away because the Cl is partial negative, and the partial negative Cl would be very strongly attracted to this very strong partial positive charge. Ibra, is this clear as well? Abba, is this clear?
Yes, sir.
Yes.
Achha, but over here, if the Cl breaks off, so over here, if the Cl breaks off and takes away the electrons, minus one, then the carbon over here has not much to worry about because its positive charge is not very strong. I mean, it can get electrons from the carbon chains that are surrounding it. Lots of electrons over here. So it would allow the Cl minus one to go away. So there are two things. So what you're going to write in your paper is, and you're going to be asked about this. What you're going to write about as an explanation for this is that, I mean, the simple explanation is that carbocations with more alkyl chains are stable, like the one over here. Like if there are lots of alkyl chains, the positive charge is not going to be very large, and it would allow or let the Cl minus one to go away. So carbocations with more alkyl chains are more stable. And over here, the Cl is so tightly bonded to this positive carbon atom that the OH minus one has to come in and push the Cl away. Otherwise, the Cl would not readily break off. So carbocations with more alkyl chains are more stable. ये उसमें हमने we did this in Markovnikov's rule as well. So tertiary halogenoalkanes so your tertiary halogenoalkanes have stable carbocations. Hence, the mechanism is SN1. While primary halogenoalkanes have unstable, like if the Cl breaks off, So over here, if the Cl breaks off, takes away the electrons, the carbon over here would get a positive charge. But the positive charge would be so large because I mean, there are no alkyl chains around it. There's only one. So it's not surrounded by electrons. So the positive charge would be so large that this carbocation would be unstable. It would immediately attract the Cl minus 1 back again, wouldn't let it go. So while primary halogenoalkanes, let me complete this. They have unstable carbocations. Unstable carbocations. That's the explanation that you're going to write. And hence its SN2 mechanism. ठीक है, is this clear? Ibrar, clear? Abar, Rida, Iba, is this clear?
Yes, sir.
So that's all about SN1 and SN2 mechanism. TK, you have and you have to remember everything about this TK that we did. And there would be three reactions. One is OH minus one, Cl minus one, and NH3 minus one. Then a few more reactions of halogenoalkanes. You have an elimination reaction of halogenoalkanes. Now, what's an elimination reaction? Now, in an elimination reaction, you have a halogenoalkane. Let's say there's Cl and there's H and H. Let's say this is H as well. Now, in an elimination reaction, the Cl, so one of the carbon atoms loses the Cl. And the immediate neighboring carbon atom loses an H. They're both gone. And the result is an alkene. So you're going to have three carbon atoms, 1, 2, and 3. And you have all these hydrogen atoms. Except that you're going to have a double bond over here. These two carbon atoms, they've lost a Cl and an H. And where did the Cl and H go? They ended up forming HCl. So that's what an elimination reaction is, and that happens when the reaction conditions are when you use NaOH, ethanolic, which means ethanol is the solvent, plus reflux. Reflux would be a better word. Plus reflux. So that's basically your elimination reaction. Okay, is this clear? A simple reaction. Abba, is this clear? Rida, Hiba, Ibrar, is this clear?
Yes.
Achha, so one thing about this reaction that you have to be very careful about is, especially when alkenes are formed. Whenever alkenes are formed, always treat cis and trans isomers as separate molecules. Okay, as an example, I'm going to show you one reaction as separate molecules. So, for example, you had 2-chlorobutane, and you were doing an elimination reaction for 2-chlorobutane. So there was a Cl attached over here, and the rest were all hydrogens. So how many different alkenes do you think would be produced if elimination happens? In this case, I mean, there's a carbon. Ibrahim, any idea? elimination is happening. Cl is going to go away. And I told you from the neighboring carbon atom, an H would be lost. Now it has two neighboring carbon atoms. One is on the right side, so an H could be lost on the right side, right? Or there's a neighboring carbon atom on the left side, so an H could be lost on the left side. Okay, so both things could happen. So you're going to get two different molecules. One would be that you're going to have carbon atoms 4 H, and the Cl is lost, and there's a double bond over here on the right side. Or you could have the other molecule could be that you have 4 carbon atoms and the double bond appears over here in the middle. The Cl and the H are lost. Abba, is this clear? Ida, Hiba, Ibrar, is this clear?
Yes, sir.
Yes.
So you're getting two different molecules. So remember this elimination reaction that the Cl would be lost, but the H would be lost from the immediate neighborhood. And sometimes the immediate neighborhood could be on the left side or it could be on the right side. So how many molecules do you get? Can you get another molecule of this? How many different? So the question is, how many different alkenes are formed? What's the answer to that?
Mm.
Like, huh? Is there even
4, 3 or 4.
why 3 and
Yeah.
4?
Because matlab including cis trans, so
Exactly. This one over here is going to form cis and trans. Okay, so this one would exist in two forms, in 3 dimensions. There would be a cis version and there's going to be a trans version. So in reality, there would be 3 alkenes. I mean, this over here has 2 cis and trans representations. So there would be 2 of these and 1 of this. This wouldn't form cis trans because for cis trans, you need the double bonded carbon atom should have 2 different groups. So over here they have the same group. So this one would not form cis and trans. This one will form cis and trans. Okay, clear है? Zida, Hiba, is this clear?
Jesus.
Yes.
Achha, plus there's another thing, sometimes there would be no elimination if there is no neighboring hydrogen atom. As an example, okay, there's a Cl on one of the carbon atoms, and the other carbon atom has carbon chains attached to it. So you're going to look at the 2 carbon atoms. The Cl would be lost, but the neighboring carbon atom has no hydrogen. There is no hydrogen attached to this one. So this one would have no elimination. So as neighboring carbon atom has no hydrogen atom. Okay, is this clear? So be very careful with this. Elimination reaction is a simple reaction. You just need NaOH, ethanolic, and reflux. The halogen would be lost and the H would be lost from the neighboring carbon atom. Except that you have to figure out how many different alkenes could be formed. Make sure you treat cis and trans as different molecules, and sometimes elimination would not happen. Okay. So is this clear? Ibra, is this clear? Abba, is this clear?
Yes.
So we'll
Yes.
continue. We'll continue with this tomorrow then. Okay.
Sir, could you please share this board link?
I'm sharing it right now. Just 1 second.
Okay, thank you.
Okay.
Allah Hafiz, sir. Thank you.
Allah Hafiz.